Hello, my chemistry folks. As you watch this, I will most likely be in New Orleans. I have recorded this in advance, as you can tell by the fact that I'm in my office. If this doesn't match up perfectly, we'll fix that when I get back. But in the meantime, I'm going to start chapter 19, which is carboxylic acids and nitriles. So far, we've been knocking out a chapter a week. We'll keep that up. So let's get to our doc chem. So the first thing we're going to look at is the properties of these guys. So carboxylic acids, acids, and nitriles. So there's two ways of writing when we just abbreviate a carboxylic acid. It's RCO2H, or alternatively, we could be RCOOH. Technically, maybe it should be RCO in parentheses OH. Probably the best way, but many of these things are the nitrile, which is our basic cyano group, is just RCN. It's understood that it's a triple bond. So we already know some properties of carboxylic acids. One, we know these guys are sp2 hybridized. Which makes them trigonal planar. They, while the cyanides, they're very electrophilic, have very electrophilic carbons. And they're sp hybridized, sp1 hybridized, so that means it's a 180-degree bond angle. So R, C, triple bond N, that's 180. When it comes to naming these guys, the carboxylic acid, or the IUPAC, the carboxylic acid is usually going to be the defining, it's one of the defining characters. I'm pretty sure it's one tops just about everything else. So we're going to find the longest chain with the carboxylic acid, with the CO2H. And then the E of the ane goes to oic acid. Or find a ring containing the acid. And the other thing to note is that the count starts from the acidic carbon. So this is a carbon 1, 2, 3, 4 from acid. So we got to make sure we start our count from the acid. That's our carbon 1. It takes the highest priority. We should have the lowest number. We can have double bonds and stuff. We can call, for example, we can talk about this. Like, oh, now it wants to die on me. this would be an enoic acid. So it doesn't have to be a it doesn't have to be a methanoic acid or whatever. In most, well, we're not going to name these this way. In most common names, it's just going to be what is the group, and then ic acid. So we learned that because if we have a one carbon, that's formaldehyde. Well, so if I change that aldehyde into an acid, that becomes formic acid. The two carbon, that's acetaldehyde, becomes acetic acid, which we all know. So it is possible to have diacids. Diacids are just a big chain with two acids in it. But if you had a diacid, you call it dioic acid, just like you'd call it a diol. So we could do that. Let's give an example of that. Let's see. I would, in this case, I'll probably call that 1, 2, 3, 4, 5, 6. 6 carbons. This gives, this would mean it's 2 methyl, then 1, 6 hexane dioic acid. The other option, or the other thing we might have to worry about, is carboxylates. If we depronate an acid, we would have a carboxylate, just like acetate. How would we name a carboxylate? Carboxylate gets named the metal, then whatever the parent compound is, and then 8. So, while we would, the common name of, we might have the common name of sodium acetate, you would call that sodium ethanoate. That'd be the IUPAC name. Sodium ethanoate. Nitriles, they're of lower priority than acids. But if we only have a nitrile, or so the IUPAC rule would be the longest chain with the nitrile. Longest chain with nitrile. And then we're gonna, let's say, add nitrile to name. So it's like a methane nitrile, or ethane nitrile. So nitrile becomes Indian. We're going to name the carbon 1 is on the nitrile, is on nitrile carbon. So once again, that's going to take precedence over many other groups. It's highly If we're doing common names, name is would just whatever the, the the common name is adds the O nitrile. It's almost like Irish. So aceto nitrile would be ethane nitrile. And if it's a substituent, if it becomes a substituent, so like for example, I have so it becomes a cyano group. So let's say longest chain. So 1, 2, 3, 4, 5. This is pentanoic acid, but the cyano, so it's 3 cyano pentanoic acid. 3 cyano pentanoic acid. So we give the acid the preference over the nitrile. But it becomes a cyano group rather than a nitrile. Now, some more properties of these guys. With carboxylic acids, I'm going to just abbreviate these guys as Ca. These guys have very strong dipole interactions, as well as hydrogen bonds. Because remember, you need the OH and this and another O. See, these guys will often exist as dimers in solution. Even so, you're going to have like, oh, here's my acetic acid. You're going to have another acetic acid. You're going to have interaction. Going to dimerize and stabilize itself. It's one of the most polar compounds you can have. So with that in mind, it's going to have a very high boiling point and a high melting point. So if we're comparing these guys together, this is probably going to be the highest one we're going to see. As far as for the carboxylic acids, if we're looking at the spectra, on the IR spectra for carboxylic acids, we're going to see a really very broad, very strong 2500 to 3500. Very broad, very strong. So that's going to be our OH stretch. We're also going to see the C double bond O. Less useful, but you should see both. In the proton NMR, you should see a proton in the 10 to 12 region. So that is way shifted. You're not going to see any of the carbon-carbon double bonds, and it's going to be a singlet. It's always going to be a singlet. This guy's not going to be coupling with anything else. This guy's pretty well isolated. It might be broad, but it's going to be there. Any adjacent, so like an acetaldehyde, this is not super useful, but this hydrogen, it might be like 2 to 2.5, but that's not super useful, but it's a little bit shifted. Now carbon-13, that's a little bit more useful. Carbon-13 For these guys, you're going to see in the region of 170 to 200. So, thing to note, 200 plus is ketone and aldehyde. Like 100 to 150 is just about double bonds. So that means there's a key region right here, which is going to be acids and esters. Acids and esters. So just by finding one carbon in this region, you immediately can go, oh, okay, very important. We have an acid, we have an ester. So you know, one, you have, that's 1 degree of unsaturation you're taking care of, and also 2 oxygens out of your molecular formula taken care of. And then if you can match an OH to that as well, great. You've taken care of one of your hydrogens signals. Now, the nitrile. Similarly, nitrile, where you expect to see in the IR, you should expect to see a C triple bond end stretch about 2250. This is in the sp1c region. Similar to that. The only problem is the triple bond of carbon-carbon is not always seen because of symmetry. But this guy, because the carbon is bound to a nitrogen, you're always going to see that stretch. So you should see that. If you don't see it, something different. There's no hydrogen, so there's no proton NMR. And carbon 13, it's in the 115 to 120 region. A little bit past what you would expect for a triple bond, but it takes care of 2 degrees of unsaturation, and there's no hydrogen attached. So, and if you have a nitrogen in your formula, that will also help things out. Now, all that is just some properties and where to expect them in the spectrum. So we're going to talk about, in this chapter, how to prepare these guys, and largely that, how to prepare these guys. And maybe some few reactions, but largely talk about preparation. Some of this stuff will be familiar, so it shouldn't be too difficult. Carboxylic acid, so like acid preparation. So I may not go into as much as I might have. So we can, for example, one method. It's oxidation of primary alcohols. In that if I use a sufficiently strong oxidant, like say like chromate, it's just going to go all the way to acid. Not going to stop. We can do oxidation of aldehydes, which is basically if a primary alcohol would have been stopped at aldehyde, we can just go the last step. Keep on oxidizing. I mean, that one's pretty straightforward. We can do the carboxylation of Grignard. Carboxylation by Grignard. That one we talked about at the end of chapter 17. Grignard. So if I have RMGX and I put in CO2 and work up with acid, it's going to slap that onto the CO2 and we have a 1 step longer chain. That's a very easy one. There's various different oxidations of alkyl benzenes, oxidations of alkyl benzenes. We talked about this at the end of our electrophilic aromatic substitution, where if I have some sort of benzyl alcohol and I use potassium permanganate, doesn't matter what, we get a benzoic acid. It cleaves off this bond at the benzyl position. So, and of course, whether we talked about this too much, is ozonalysis of an alkyne. Ozonalysis by an alkyne. Ozonalysis of alkyne. So, alkyne. Remember that a ozonalysis breaks double bonds and the sigma bonds attached and adds a oxygen there, usually as a aldehyde. Usually as an aldehyde. Well, if I have a R, C, triple bond C, R prime, and I do the ozonalysis and the workup, this what like C3S, something like that, you're going to get RC, going to cleave through 2 double bonds and the sigma to make a triply oxidized species, and we're going to get 2 different products if it's a non-symmetrical alkyne. So, those are some methods we've already learned. Before we go any further. Now, some other things to note. That this one should be obvious, that carboxylic acids are a strong Bronsted-Lowry acid. Lowry. Oh, sorry, they're strong Bronsted-Lowry acid. So they will be deprotonated with a base of a higher pKa. Right. Base of higher pKa. So we're looking at the pKa strength. Most carboxylic acids will have a pKa of about 5. So anything with a pKa greater than 5 will, if it's a base, it will deprotonate. So here are some common bases and their relative pKa's. So some of these will be familiar. So common bases. So bicarbonate with carbonic acid having a pKa of 6.4. So already off to a good start. That guy will deprotonate. Ammonia with ammonium, pKa of 9.3. It's a base. Yeah. Carbonate, proper, not bicarbonate, which will undergo to form bicarbonate, is 10.2. Hydroxide, which will reform water, has a pKa of 14. So then we're starting to get into some organic stuff. Methanoate, not methoxide, which is the conjugate base of methanol, 15.5. 15.5. So that's slightly more basic than water. Ethanoate. Sorry, not ethoxide. Ethoxide, not ethanoate. Slightly more basic still. It's ethanol. It's at 16. And a really strong base, hydride, which when it deprotonates forms H2. It has a pKa of 35. We've also looked at things like the methyl carbanion has like a pKa of like 50. So there's lots of things that will deprotonate this. Now, why does this guy have such a low pKa compared to everything else? It's because the deprotonation leads to a resonance stabilized conjugate base. This is why it's so much more acidic than any alcohol. Because remember, anything that stabilizes the anion makes something more acidic. So, being able to say CH3 O being able to resonate these two structures means we're stabilizing that negative charge. So, just a quick example. Ethoxide versus ethanol. It was like the ethanol is weaker than acetic acid, but phenoxide versus phenol. This guy can be resonance stabilized. This guy is mildly acidic. Let's draw the Kekulé structure so we can see this. Resonate. I'm not going to bother to draw the simple conjugation, but like, okay. And then I can resonate. I'll draw the other one more structure, or resonance structure, because otherwise the other one is just the invert of that. But let's draw the other resonance structure, which is unique. So putting the lone pair on that carbon. So we have a third one. Oh, fine, I'll draw it. Just for the sake of completeness. So that guy ends up being stabilized. So it is more stable than ethoxide, but actually less stable than acetate, as the charge is delocalized on carbon rather than delocalized on oxygen. So if I wanted to put like acetic acid, acetic acid is more acidic. It says then phenol, which is more acidic than ethanol. But this guy is definitely acidic. Now, it's not a strong acid. It's much weaker than acetic acid, but it is acidic. So the key here is the absolute number of resonance structures is not the most important thing. This guy has 4 resonance structures, while this guy has only 2 resonance structures. It's the effectiveness of the resonance structures. This guy is still the prime contributor because we're putting a negative localized negative charge on carbon as opposed to between 2 oxygens. So now, if there is an electron withdrawing group present, this will stabilize the conjugate base, and which will increase acidity. So for example, CF3, so trifluoroacetic acid is going to be far more acidic than just normal acetic acid because induction is going to pull out electron density from that resonance, the acetates, and thus stabilize that more. And of course, if electron withdrawing groups stabilize, electron donating groups will destabilize the conjugate base and decrease acidity. So paranitrophenol would be very acidic, while having something like let's say we'll just say paramethylphenol would be less acidic because it's the methyl would be electron donor, not a very strong one, but it would have an effect. Now, in general, the more electronegative groups you have, the more electronegative the group, the more acidity. The stronger the electronegativity, the more the acidity. The closer they are to the acid, the more the acidity. So, for example, CF3CH2 acid is going to be less acidic than CF3 because they have to pull electron density from further away. If I wanted to compare CF3COOH, that's going to be stronger than CF2HCOOH, which is going to be less strong than CFH2COOH. The more the electronegative groups on there, the greater the acidity. If I had CCl3, COOH, that's going to be less acidic than CF3. So all these just going to be, this should make sense in terms of what we've learned in chemistry. not organic chemistry, in general chemistry. Recall back to your 112. Your 112, we learned about acidity. We learned about that what makes a strong acid, what makes a strong base. Resonance structure, stabilization of the conjugate base. So all this is old hat. Okay, with that in mind. So talk about substituted benzoic acids. I already kind of talked about that, but with substituted benzoic acids, with substituted benzoic. Okay. So the key thing is electron donor groups tend to destabilize the conjugate base. Base decreases acidity. Yeah. Electron withdrawing groups will stabilize the conjugate base and thus increase acidity. So here's an example group. So the substituents, what can we have? We can bring them down to electron donating. We have our amines of all types. Then we have our alcohols, our ethers, our amides, or amides, and our alkanes. These are all activating groups and thus makes it less acidic. So, and then, of course, our electron withdrawing groups. We have our halogens, we have our aldehydes, we have our ketones, we have our esters, we have our acids. Sorry, I'm going a little low. We have our cyanides, we have our sulfates, and then nitros, and finally ammonias, and our 3+. These are all deactivating, and thus makes it more acidic. So acidity is increasing as we go down. Now, with that in mind, knowing that we have a group present that is acidic, and we can depronate it, there's an extraction technique we will often use. Extraction technique. So if you have a carboxylic acid, we can use extraction technique to remove our acids from our solution very easily. Now we're going to separate things separated by the solubility differences. Separated by solubility differences in aqueous and organic solvents. So this is where we're going to bring in the separatory funnels. I mean, do you have to do this? No, but it's one really easy way. Step 1. Deprotonate acid. Acid with a base. And so organic shifts to ionic. So acetic acid may be mildly soluble in things like ethanol or in other organic solvents. But when you deprotonate it, the solubility decreases. Not soluble in organic. Okay. So we have that. So sodium hydroxide won't deprotonate alcohols. Yeah, it might do some stuff to esters. But so essentially, so this is effective enough for separation. So with that in mind, a separatory funnel, the purpose of that being we can shake this up, we can get a good separation. We got an organic layer, we got an aqueous layer. If we have a good split level between the two, then what we're doing is we're then like separating them based on densities. We extract the organic layer into one flask, we extract the aqueous layer into another flask, and then we could go on and reprotonate, put a weak acid in there to reprotonate our acid, and then the solubility changes again, and we can get an organic. Maybe we're going to use some sodium sulfate to dry up the rest of the water or whatever. But the idea is that if we can make a layer, a big separatory funnel, gotta stop cock, and we have a, say maybe have organic, aqueous, we got our solvents and our starting material back in here, and we got our product in there, separate the product, and then dry it out, and that saves us a lot of time on workup. So we don't have to separate a lot of the starting material. But okay, that's where I'll stop for this first video.